Let us try to understand what equilibrium is through a simple observation. Look at the closed container with a small amount of liquid bromine. What do you observe? You observe that some of the liquid bromine is evaporating to an orange vapor, and slowly the vapor becoming thicker. After some time, you can see that there is no change in the intensity of the vapor anymore, and also that a small amount of liquid bromine is left in the flask. How do you explain this? Here's the explanation. All the molecules in a liquid do not have the same kinetic energy. Some molecules at the surface of the liquid that possesses a relatively higher kinetic energy escape from the surface into the vapor phase. When the air inside the container is saturated with vapor, the molecules in the vapor phase condense to liquid as fast as the liquid evaporates. After some time, the number of molecules evaporating from the surface in a given time becomes equal to the number of molecules condensing on the surface during the same time. At this stage, equilibrium is said to have been established between the liquid and the vapor phase. This is why we see that the color of the vapor in the flask does not change. Thus, equilibrium may be defined as a condition in which two opposing tendencies balance one another. The equilibrium of liquid bromine with its vapor may be represented as Br2 liquid in equilibrium with Br2 gas. The pair of half-headed arrows indicates that the two processes, evaporation and condensation, are occurring simultaneously. At equilibrium, the rate at which the particles move from the liquid to the vapor phase will equal the rate at which the particles move from the vapor phase to the liquid. In this situation, the concentration of the vapor particles in the air space will be constant even though there is movement in both the directions. This equilibrium is, therefore, known as dynamic equilibrium. The opposing tendencies of a reversible change continue to take place with equal rates simultaneously at the equilibrium stage also. Hence, the equilibrium is called dynamic equilibrium. Equilibrium can be established for both physical and chemical processes. At the equilibrium state, if there is a change in the physical state, the equilibrium is called physical equilibrium. The important aspects of equilibrium involving physical processes can be understood by studying some phase transformation processes, such as solid-liquid, liquid-vapor, solid-vapor. Let's see solid-liquid equilibrium. Ice in equilibrium with water in a perfectly insulated thermos flask at 273 Kelvin and at atmospheric pressure stands as a perfect example of solid-liquid equilibrium. For this equilibrium, you can see that the temperatures as well as the masses of ice and water remain constant. Why is this so? Ice-water equilibrium is a dynamic equilibrium, where the number of molecules going from ice into water and the number of molecules going from water into ice are equal. As the rates of transfer of molecules from water to ice and from ice to water are equal, there is no change in the masses of ice and water. Since the system is insulated, no exchange of heat between the system and the surroundings is possible, and hence the temperature remains constant. The equilibrium for this phase change may be written as H2OS in equilibrium with H2OL. It is important to note that ice exists in equilibrium with water only at a particular temperature and pressure. Thus, for any pure substance at atmospheric pressure, the temperature at which the solid and liquid are at equilibrium is called the normal melting point or normal freezing point of the substance. Let's now look at liquid-vapor equilibrium. Water in equilibrium with vapor in a closed vessel serves as a classic example of liquid-vapor equilibrium. Let's understand this through a simple experiment. A small amount of water is taken in a closed vessel to which a manometer is attached and left undisturbed for some time. After some time, you can see the slow increase of the mercury level in the manometer and the final attainment of a constant value. Did you also observe that there is a decrease in the volume of water in the vessel? How do you explain this? In the beginning, there was no water vapor inside the vessel. As water evaporated, the pressure inside the vessel increased, which was indicated through the rise in the level of mercury in the manometer. After some time, the level of mercury in the manometer remains constant, indicating that a state of equilibrium has been attained between water and water vapor. The molecules of the vapor in their movement collide with other molecules, with the walls of the container as well as the surface of the liquid. When some of the molecules with less kinetic energy come closer to the liquid surface, they get attracted to the surface. This process is called condensation. At any given temperature, evaporation and condensation take place simultaneously. After some time, the rate of evaporation becomes equal to the rate of condensation, and then liquid-vapor equilibrium is established. The pressure exerted by vapor over a liquid when it is in equilibrium with the liquid at a given temperature is termed as the vapor pressure of the liquid at that temperature. Water exists in equilibrium with its vapor at atmospheric pressure in a closed vessel. Thus, for any pure liquid at 1 atmospheric pressure, the temperature at which the liquid and vapor are in equilibrium is called the normal boiling point of the liquid. Let's look at solid-vapor equilibrium now. Some solid substances directly undergo a phase change from solid to vapor without the intermediate liquid state. This is called sublimation. Observe the solid iodine placed inside the conical flask and fitted with a cork. You can see the vessel getting filled up slowly with violet vapors. Have you observed that the intensity of the color has become constant? At this stage, we can say that an equilibrium state has been attained for the system. At equilibrium, the solid iodine sublimes to give iodine vapor, and the iodine vapor condenses to give solid iodine. The equilibrium can be represented as I2 solid in equilibrium with I2 vapor. You have learned that during physical process like phase transformation, it is possible to attain equilibrium. Similarly, when a physical process like dissolution is taking place, it is possible to achieve a state of equilibrium. There are two types of dissolution: gas in liquids and solid in liquids. Sugar in water is a classic example of solid in liquid equilibrium. First, sugar is added to a glass of water and stirred. It dissolves, forming a sugar solution. Then, as more and more sugar is added, it initially dissolves, but eventually reaches a stage where no matter how long you wait or how vigorously you stir, the sugar does not dissolve. The solution thus obtained is said to be saturated at the given temperature. Thus, at a given temperature, a solution that remains in contact with excess solute is said to be a saturated solution. In a saturated solution, a dynamic equilibrium exists between the solute particles in undissolved state and the solute particles in the solution. When the solution is kept in a closed system, the concentration of the solution and the amount of undissolved solute remains constant in the solution. The dynamic nature of this equilibrium can be established using radioactive sugar. Let's see how. Take a beaker containing saturated sugar solution. To this, add a small quantity of radioactive sugar and let the solution remain undisturbed for some time. Then check the solution for radioactivity. It is noticed that both the undissolved sugar as well as the solution has turned radioactive. This is a result of dynamic equilibrium, where the molecules of the radioactive and the non-radioactive sugar from the solid and liquid phases are being exchanged. This proves that there is dynamic equilibrium when a solid is dissolved in a liquid. Now let's look at the equilibrium involving the dissolution of gases in liquids. Have you ever wondered why soda fizzes when opened? The fizz that bubbles up when you open a soda water bottle is carbon dioxide gas. The phenomenon of fizz you see in carbonated beverages is due to the difference in the solubility of carbon dioxide at different pressures. At a given pressure, equilibrium exists between the carbon dioxide molecules in the gaseous state and those in the dissolved state in the liquid. This equilibrium is governed by Henry's law, which states the mass of a gas dissolved in a given amount of a liquid at any temperature is directly proportional to the pressure of the gas present in equilibrium with the liquid. All carbonated drinks are bottled under pressure to increase the solubility of carbon dioxide in the solution. When the bottle is opened, the pressure above the solution decreases. To reach the new equilibrium condition under decreased pressure, some of the dissolved carbon dioxide escapes. This gives rise to the fizz that you see when you open a bottle of carbonated drink. This is also the reason why the taste of carbonated drinks turns flat when the bottle is kept open for some time. Thus, we can summarize the general characteristics of equilibrium in physical processes as: at atmospheric pressure, a solid exists in equilibrium with a liquid only at one temperature, which is called its melting point. For example, at atmospheric pressure, ice exists in equilibrium at 273 Kelvin. At a given temperature, vapor pressure remains constant for liquid-vapor equilibrium. For example, in equilibrium between water and water vapor, the vapor pressure of water remains constant at a given temperature. At a given temperature, solubility remains constant for the dissolution of solids in liquids. For example, at the given temperature, the solubility of sugar remains constant in a given liquid. At a given temperature, the concentration of a gas in a liquid is directly proportional to the pressure of the gas over the liquid. For example, the concentration of carbon dioxide in water at equilibrium is directly proportional to the pressure of the gas over the liquid. At a given temperature, equilibrium can only be achieved in a closed system. For example, no equilibrium is attained when water in a beaker is kept open to the atmosphere. This is because the rate of condensation is much less than the rate of evaporation. At equilibrium, both the opposing tendencies occur at the same rate, and hence, a dynamic yet stable status is established. For example, for water at a given temperature in a closed vessel at equilibrium, the rate of evaporation is equal to the rate of condensation. At a given temperature, the attainment of equilibrium for a physical process is characterized by a constant value of one of its parameters, such as vapor pressure, melting point, solubility or concentration. For example, during equilibrium between liquid and gaseous water molecules, the vapor pressure of water remains constant at a given temperature. At equilibrium, all the measurable properties of the system remain constant. For example, for the solubility of solids in liquids, the solubility remains constant at a given temperature.